to the third video in this session, this series of using integration with problem solving. In the last couple of videos we looked at different methods that we use to help us solve it, so finding the initial condition or using an unknown value with definite integrals. This time we're looking at something that's a little bit different. Again, we're looking for those initial conditions that help us work out the function, and then once we get that function we can work out our answer. So let's have a look at this, this example here. We've got the water pipe cross section has an inner radius of 3 centimeters and an outer radius of 6 centimeters. Within the pipe, the water temperature is maintained at 100 degrees. Within the metal, the temperature falls off at the rate dt over dx is equal to negative 20 over x to the power of 0.63, where x is the distance from the center axis and our distance is between 3 centimeters and 6 centimeters. So find the temperature of the outer surface of the pipe. So we need to find, we've got all this information. Unlike the last example we had steps to us to do, we've got to take these steps ourselves. So in order for us to be able to find the temperature of the outer surface, we've got to work out, well, what is the actual temperature of the pipe itself? So we know that we have the integral of negative 20 over x to the power of 0.63 dx. This here is what the rate that the water is falling in temperature is. So we want to integrate this. If we integrate this here, we get negative 20x to the power of negative 0.63. And if we then put this as dx, because we're going to bring everything up, we're now ready to integrate. So if we integrate, we're going to get negative 20x to the power of 0.37, because we're adding 1 to it, all over 0.37 plus c. So if we integrate this out, and we've got this answer in terms of t of x. However, we've got that constant integration again. In the last video, we seem to be able to work out what that initial condition was, because it said 0 plates and negative 650. Here, we have a couple of values we're working with. We've got 100 degrees, so we know that the temperature, when we look at this, is maintained at 100 degrees. We also know that the inner wall is 3 centimeters, and we're trying to find 6 centimeters. So x must have to equal 3, because that's where initially we're starting from. So the temperature initially at 3 centimeters is 100 degrees Celsius. And because we're trying to find the temperature of the outer of the structure, so for instance, if I was going to draw a picture of this, we've got 3 centimeters here, we've got 6 centimeters here. So we know that at 3 centimeters, it's 100 degrees. What we don't know is what is it at 6 centimeters. We do know that it's decreasing, and we do know that initially at 3 it's this. So therefore, here are my initial conditions. So I can now put this information in. I have 100 is equal to negative 20x, 0.37, or actually we're not going to put x there, are we? We're going to put 3 to 0.37 over 0.37 plus c. Well, let's work this out here. If we have 20, let's get a calculator. I'm not going to do that in my head. This is just too late in the day for that. So negative 20 brackets, 3 brackets, the power of 0.37, 37 equals divided by 0.37. We get 100 is equal to negative 81.16 plus c. Well, we want to find c by itself, so let's add them. So therefore, c is equal to 181.16. So therefore, t of x is equal to negative 20 x to 0.37 over 0.37 plus 181.16. So there is our function for us to be able to work out, well, we know it at 3 and 100 gives us this function. Well, what's the temperature going to be at 6? So therefore, we can substitute this in and we'll get, when we put 6 in, we get negative 0.37 over 0.37 plus 181.16. If we plug that in, before we do that in our calculator, let's have a think about what we think the answer is going to be. We've got some clues in this information. It starts at 100 degrees at 3 centimeters, and it says it falls off. So when it says falling off, it's decreasing. And another thing it tells us it's decreasing is the rate. The rate in temperature in terms of the distance is minus 20. So therefore, our answer we get here, we should be thinking in the back of our head, well, it's got to be less than 100 because it's fallen off. And if we don't get less than 100, then we've done something wrong here. So have these kind of things in the back of your head, thinking about the maths, thinking about, how do I know I'm on that right track? So let's plug this in. I already got an answer up here ready, do I? No, I don't. So let's put it in. Brackets, 6 brackets, power 0.37 over 0.37 plus 181.186. We get approximately 76.3 degrees Celsius. So that's an approximate. If we wanted to go to an exact answer, if we went to 3 significant figures, we just have, well, that's not 3 significant figures, so 76.3 degrees Celsius. We know this is on the right track because we just said it should be less than 100 because it's falling. So in this question, as opposed to the last couple of questions, we had to pull that information out. We had to think about, well, what is it asking us to do? We know we've got a derivative. We've got to find that temperature. So the dt and dx means that I need to find the temperature in respect to distance, or x in this case. I integrated it through, I ended up with that constant, so I then had to come back and go, well, where is my initial information in this question? We looked at that diagram, how we can see at 3, where it initially was 100 degrees, I couldn't use 3. I had 100, I had 3, and I had 6. All I know is that the answer is asking me for the outer temperature, and that's it here, 6. So therefore my initials could be 3 and 100, plug it in, get my C value, and then I can work out what the temperature is going to be at 6 centimeters. So that will conclude our little series on problem solving. I hope it's helped you. Have a look at the questions, have some fun. Just remember that we are looking at trying to find the primitives or the derivatives of our primitives of our derivative functions.